Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we cover all things Gen Chem related. On this video, we're going to be learning different ways we can calculate the concentration of solutions. Let's get started. So if you recall, we learned about concentrations and ways to describe the concentration of a solution back in chapter 4. So if you haven't already watched that video, you may want to go back and revisit those videos on molarity and things of that nature. But basically, when we're describing the composition of a solution, we often want to define what's the concentration. Well, the concentration is really describing the relationship or the amount of solute compared to the overall solution that is present. Now, we do have qualitative terms that we can use like dilute or concentrated, where dilute means there's a small amount of solute present, concentrated meaning there's more solute present in that solution. But we could also calculate at a quantitative value to describe the composition of these solutions. So one of the main ways that we learned back in chapter 4 was to calculate the molarity of something. So if you don't remember the molarity formula, it's shown for you here. Your molarity is simply calculated by taking the moles of a solute divided by the liters of the solution present. And we can use this to make predictions about how much solute is present in a solution if we know the molarity, or even figure out how many, what the concentration of an ion might be if we're dealing with an ionic compound. So just to remind you, ionic compounds, when they're placed into solution, remember they ionize and they dissociate. You have your ions, your cations, your anions that ultimately end up just kind of floating around in solution. Well, if we know the molarity of the solution, we could use that in the mole ratios to predict what would the concentration of a specific ion be. So for instance, if we know we have like a 1 molar calcium chloride solution and we have 1 liter of it, well, that would mean if that's placed into this water, that we would end up getting 1 mole of calcium ions out and 2 moles of calcium ions out as well, because of that 1-to-2 ratio. Now, we have a couple of other ways that we can define the concentration of a solution. So one other way that we're going to talk about right now is known as molality. And no, that's not a typo. It's not supposed to say molarity. It is indeed molality. Now, molality has the symbol of a lowercase m. So that would be a kind of a thing to look out for on a test, is that lowercase m versus the capital M like you see in molarity. So the molality is now looking at the relationship to the moles of solute that's present compared to the kilograms of solvent, so the mass of the solvent. Now, the reason that this is beneficial is because the molality is not going to vary with temperature, similar to how the molarity might, because this is based on masses and not volumes. Another way we can define a solution is by describing a part to whole scenario. And so when we're dealing with parts, like counting the part of something, like how much solute is there compared to the whole thing, we can be measuring this in either mass or volume. And so a lot of times you'll see mass to mass percents given out to you, or mass to volume percents, or even volume to volume percents. And when we're looking at that percent simply means that I have whatever the number is, that many, let's say it's a mass to mass percent, that many grams of something per 100 grams of that solution. And so the part to whole idea is often used for percentages, as we know, where we take the part to whole times 100. But we could also apply this same theory for parts per million calculations, where now we're, instead of multiplying by 100, we're multiplying by 1,000,000. Now, this parts per million is used a lot for really, really dilute things. A great example, if you've ever worked at a swimming pool or have a swimming pool and you're adding chlorine to that water, you only add a really, really small amount for the entire pool. And so the number that's often listed on the bag may be written as like 5 ppms. And they do that because it's a lot easier to say 5 ppms, which means 5 grams for every 1,000,000 grams, as opposed to saying 0.0000, all those zeros, 5 grams. Okay, so just something to think about. So if we're dealing with percent concentrations, again, we're looking at a part to whole ratio, and we multiply by 100. And if it's a mass percent, it's the mass of solute compared to the mass of solution. If it's mass to volume percent, that's mass of solute, the part, compared to the total volume of solution. And if it's volume to volume, it's volume of solute to the solution. Again, the part compared to the whole. For parts per million concentration calculations, it's the same thing. The only difference is that now we're multiplying by 10 to the sixth, a million, as opposed to that 100 to get us a percent. Okay, and guess what? We also are going to have something called ppb, which is parts per billion, which means we're multiplying by a billion. So it's the same scenario. Again, with ppms, we're dealing with really, really dilute concentrations. And so you're looking at a gram per 1 million grams of solution. So very, very small amount that you'd be looking to calculate there. All right. And then, like I said, parts per billion, ppbs, we're multiplying by a billion, so 1 to the 9. And if it was parts per trillion, we're ppts, we're multiplying by a trillion. Okay, so same part to whole scenario. Now, we can use these concentrations, all the ones that we're talking about, percent by mass, molarity, molality. We can use any of these as conversion factors. We learned about that given and find method back in chapter 1, and I'll revisit it here for you real quick. So remember, if you're given some units and you want to solve for some units, you would look for that relationship through the units by putting your given units on the bottom and what you're solving for up top. And so we can do the same idea with these concentrations that we're dealing with. We just have to bear in mind, what is that concentration describing? Is this my moles? Is this the solution? And make sure you're adjusting things accordingly. But for instance, if we had something that said it's 12% M over M, so that's M over M means mass to mass percent. What that would mean is, well, sugar, it says sugar and aqueous. So sugar, we know, will be our solute. Aqueous tells us this is dissolved in water, so that's our solvent. So what 12% M over M means that I have 12 grams of sugar for every 100 grams of my total solution. If we had mass to volume percents, the ratio would be 5.5 grams to 100 milliliters of solution, and volume to volume. So we can use these concentrations to become conversion factors for us. All right, so let's try this example. And there's a piece of information that we are going to need here, which is the density. So it says, what volume of 10.5% by mass of soda contains 78.5 grams of sugar? So our goal is to find a volume. And it doesn't specify the unit, so maybe we'll think milliliters. And we're starting with 78.5 grams of the sugar. Now remember, the sugar would represent our solute or the part. And we now want to connect from our sugar to the volume of the total solution. And so we would follow a series of steps to go from the grams of solute to how many grams of solution we have. And then if we know the grams of solution, we would be able to get to the volume of solution because we have the density. Again, the density would have to be given to you in this problem. So after that, once we've made our connections, it's a matter of setting things up. So we would take our 10.5% and write it as a conversion factor, which basically says for every 100 grams of solution I have, I would have 10.5 grams of sugar. So we would say 10.5 grams of sugar on the bottom, because we want to get rid of that, is to 100 grams of solution on the top. And then we would go from grams of solution. Well, now we know the density is 1.4 grams of solution for every 1 milliliter of solution. And then we can solve our answer. So when I plug this into my calculator, make sure you're multiplying across the top and dividing by the bottom, anything on the bottom. What you should end up getting is 719 milliliters as your final answer. So go ahead and check that, and then we will move forward. Awesome. All right. We can also use these concentrations to help us to figure out how we would go about preparing a solution. And so when we're tasked with going into a laboratory and preparing a solution, we need to know how much of this solute do I need to weigh out? What volume is this solvent? What's the total solution volume that I'm going to? And so we can use all that information to help us to calculate what would be the amount of solute that I might need in order to prepare a solution. All right, so if we look at a problem like this where it says, how would you prepare 250 milliliters of 19.5% by mass calcium chloride? And it tells us that the density is 1.18 grams. Now, what this doesn't say very explicitly is like, hey, you need to figure out how much solute is there. But that's ultimately what we need. We need to know if I want to make 250 milliliters of a solution, I need to know how much solute do I need to weigh out, okay? And so if we start with our 250 milliliters, and again, that's of the solution, we could first use our density to get us from milliliters of the solution to grams of the solution. And so that would be our 1 milliliter on the bottom and 1.18 grams of solution on the top. Then now this is where we would want to take our mass percent and rewrite it as a conversion factor to allow us to calculate what that mass would be. So we could take the fact that it's 19.5% by mass tells us it would be 19.5 grams of calcium chloride for every 100 grams of solution. So 100 grams of solution is to 19.5 grams of the calcium chloride, our solute. Okay, if you're struggling with doing these conversions and not sure where to put what units, go back to my videos from chapter 1 where I discuss dimensional analysis, or that given and find video, and that'll help you out. So when we plug this in, we're going to do 250 times 1.18 times 19.5. And when we do this, we end up with 57.5 grams of calcium chloride would be needed. Okay, so check your answers and hopefully we are ready to move on. If not, pause it. All right. One other way we're going to talk about how we can define a solution's concentration is through this idea of mole fraction. Now, we learned mole fraction back in chapter 5 when we were dealing with vapor pressure and Dalton's law and partial pressures. So just to remind you, the mole fraction is the fraction of the moles. So we're taking the moles of solute compared to the total moles that are found in solution. Remember that mole fraction will be unitless. And the total of the moles of the mole fractions, when we add up the different mole fractions for each substance that's present, should add up to 1. And we can also calculate something known as the mole percentage, which is just simply a percentage of the moles. So you just take your mole fraction and multiply by 100. Okay. All right, so we're going to put all that I just talked about together in a series of several problems. It's like 4 that we're going to go through. Now, what you're going to notice, the numbers that we're dealing with that are provided for us are the same in every single problem. But what we're solving for is different. And this is intentional so that you can really focus on, okay, what's the information I need to address this question? Sometimes they give you a lot of information that you don't need, okay? So just keep that in mind. So this one says, what is the molarity of a solution prepared by mixing 17.2 grams of C2H6O2 with 0.5 kilograms of H2O to make 515 milliliters of solution? So if we're looking for the molarity we know is going to be the moles of the solute divided by the volume in liters of the solution. Okay, and so we got to look and see, do we have the information needed? Well, I do see we have a volume of solution, so that's good, but it's not in liters. But we can do that really easily. Just simply divide by 1,000 or move that decimal point 3 places. So that would become 0.515 liters. But we don't have the moles of solute. But what we do have, we have the gram amount, that's 17.2 grams of C2H6O2. And we know from back in chapter 2, how we can calculate the number of moles that are present by using that molar mass. So we'll calculate the molar mass of that substance. So we need 12.01 for carbon, but there's 2 of them, plus 1.01 for hydrogen, but there's 6 of them, plus 16 for oxygen times 2. And that gives a total of 62.08 grams is to 1 mole. When we plug that in, we get 17.2 divided by 62.08, And that gives us a total of 0.277 moles, okay, of the C2H6O2. All right, so then once we've done that, to figure out the molarity, we're going to take those moles and divide it by the volume in liters. Okay, so 0.277 divided by 0.515, and that gets us a total of 0.538, and that would be capital M for your answer. Now, write that number down if you are following along with this series, because we're going to be doing, like I said, 4 different problems, and we're going to be we can compare the answers as we go along. Okay. So this one says, what is the molality? The molality of a solution prepared by mixing 17.2 grams of C2H6O2, all the same variables. Well, now the molality, remember the molality is not a typo. The molality is a real thing where we're looking for the moles of solute divided by the kilograms of solvent. And so we know the moles. We actually just calculated that in the previous example. So our moles, I'm not going to recalculate it, but we know it's 0.277 moles because that's still my solute. And then our solvent, well, if this is our solute, the water must be our solvent. So we're going to need this 0.5 involved. So for the molality, we're going to take 0.277 moles divided by our kilograms of 0.500 kilograms. And that gets us 0.554 lowercase m. Now, if we compare that to our previous answer of 0.538, you see they're pretty close. And I guarantee if this is a multiple choice question, both answers would be an option. So just make sure when you're doing this, you've read the problem, you're solving for the proper thing. In this case, that being our molality. The next problem is asking us, well, what is the percent by mass? Percent by mass of a solution prepared by mixing 17, so all the same stuff. So remember, if we're doing the percent by mass, that means we need the mass of the solute compared to the mass of the solution, not just the solvent. So we have the mass of the solute. A lot of people might be like, oh, and we also have the mass of the solution. But remember, that water is not the solution. That water is just the solvent. So to get to the mass of solution, we would need to add those two. So we would take 17.2 grams plus, and you got to make sure you convert that to grams first. So divide by 1,000, multiply by 1,000 to get 500 grams. So that would give us 517 grams total. So our mass percent would end up being 17.2 grams divided by 517.2 grams times 100. When we plug that in, 17.2 divided by 517.2, and that gives us, and multiply by 100, that will give us 3.33% as our mass percent. Okay, again, key here was recognizing that we needed to figure out what the mass of our solute was. And then this one is asking us, well, what's the mole fraction of the solution prepared under those same terms? Again, we already know the moles of this from the previous chapter. That was 0.2, or previous problem, that was 0.277. Now, mole fraction, we know is the individual moles, the moles of the solute, compared to the total moles. Okay, and so we have the moles of the solute. What we don't have is the moles of the solvent in order for us to add the two together. So we can take our solvent, that 0.5 kilograms of water. We first get that to grams. So that would say 1 kilogram is to 1,000 grams, or 10 to the third. And then if this is water, we would say that 18.02 grams of water is for every 1 mole of water. Okay, so all of these are water here. So we have 0.5 times 1,000 divided by 18.02. And that'll give us 27.7 moles of our solvent. Now, again, that doesn't go into our calculation. We need to figure out what our total moles are, or the solution moles. So we would take 27.7 plus 0.277. And that gets us 27.977. We'll deal with sig figs later. All right, and so that's what goes into our problem. So we would take our individual moles, 277 moles, divided by, that looks crazy, 277 moles divided by 27.977 moles. And so we would then take 0.277 divided by 27.977, and that gets us 0.00990 times, not times 10, anything. That's it. And it's unitless. Remember, mole fraction is the unitless. Okay. Awesome. Or you could say 9.90 times 10 to the negative 3 would also work if your calculator is giving it to you in scientific notation. Check with your teacher to see what they prefer. I'm indifferent on which route my students give it to me. In the last iteration of this problem, well, this is asking us for the mole percent. So the mole percent is exactly the same thing that we just did, but now we're going to take those values and multiply by 100. And so it would essentially be taking that 0.00990 times 100, and that's going to get us 0.9 90 as our mole fraction percent, our mole percent. Okay. So go back to the last problem if you need to write it down. We've done a lot in this video, I recognize, but hopefully as you're going through this, these problems start to get a little bit more comfortable for you. And so the last thing we're going to just talk about is just how we can convert amongst or from one unit to another, like from the mass percent to the molarity, or from the molality to the molarity. And this is possible. You just really want to be aware of, while you're doing these conversion steps, that you only focus on the numerator and the denominator independently. So as you're trying to adjust the solute portion, which is the numerator, and adjust the solution or the solvent part, which is on the denominator, you want to treat each part independently and focus on getting that adjusted before you focus on the other one. It'll make your life so much easier. Okay, so making sure you write down your units will be critical here. All right. Now this chart, it may help you. It might also intimidate you. So use it at your will. But this just shows you how all these different units that we talked about, mole fraction, molality, molarity, parts by mass, part to whole ratios, how these are all interrelated. And so this could be a good study tool for you. But I also understand if you're not comfortable with using it. Okay. All right, so we're going to do one last problem where we focus on converting from one type of unit to another type of unit. And so in this problem, it's asking us, what is the molarity of a 6.55% by mass glucose solution? All right, so molarity. Molarity means that we want to ultimately end up in units of moles of the solute, which in this case is C6H12O6, over liters of the solution. That's our goal. There should also be a bit of information here provided for us about the density. Yes, and the density for us is going to be 1.03 grams per mole. So I'm going to write that here, grams per milliliter, excuse me, so that we can use it. Okay. And so Our starting point, though, is the 6.55% by mass. And so what that would mean is that we have 6.55 grams of C6H12O6 for every 100 grams of solution. Okay, so we're going from one to the other. Okay, so what we're stressing for you to do is to focus on the numerator, the top part, first, and then focus on the denominator to try to get those to be equivalent to what you're ultimately solving for. So if I just focus on the top part, which is going from grams to moles, that's easy. We know we use the molar mass. And so we would set that up accordingly. And so we would calculate the molar mass first. So we would take 12.01 times 6 plus 12 times 1.0 plus 16 times 6. And that would give us a total of 180.18 grams of that compound, the glucose, to 1 mole of the compound. And so that top portion is already, it's matching what we need, the units align. So now we focus on the bottom portion. Now we're in grams of solution. We want to get to liters of solution. And so this is where that density is going to come into play. The density, which is 1.03 grams per milliliter of solution, give myself a bit more space. We could then put our grams of solution now is going to go on the top because we want to cancel that out on the bottom. So there's 1.03 grams of solution for every 1 milliliter. And then we got to get from milliliters to liters. And so we can add in one more where we have 1 liter on the bottom is 10 to the third milliliters and set that equal. Okay. So now we put all this in our calculator. We have 6.55 times 1.03 times 1,000 divided by 100 divided by 180.18. And that gets us a total of 0.374 molarity. Okay, so a lot of steps there, but it's not too difficult if you keep track of those units. I hope this video helped you guys understand all the different ways that we can calculate the concentration of a solution. Make sure you guys like, comment, and subscribe, and let me know what other videos you would like to see. And make sure you guys check back in for more videos in the future. Have a great day, and I'll talk to you later. Bye-bye.